Hello and welcome to Physics 1401. Today we're gonna finish the concept of chapter about work and energy. So it's part 2. It's about potential energy. Last time I talked about the definition of work, basically force times distance, or the force vector and the scalar product of it with the displacement vector. And we talked about kinetic energy and work energy theorem, which can be summarized as the total work done on an object is equal to its change in its kinetic energy, where kinetic energy is given as 1/2 mv squared. Okay. Now, I also talked about what happens when the force changes with distance. That would be the area under the force, right? That's work done. Okay, so let's talk about potential energy today, another form of energy. Now, to understand that, let's begin with an example. Okay, I think last time I talked about the work done by gravity, by, when I'm lowering the keyboard like this, mgh was the work done by gravity. If I'm lifting it up, that would be negative mgh. So let's take that example again and analyze it a little bit more clearly, like using coordinates, for instance. Let's pick a coordinate system. The horizontal coordinate is irrelevant at this point, so let's just use the vertical. Okay, so this is our y-axis with some origin that we pick. That's y equals 0. Okay, so I'm holding the keyboard or whatever I have right here. This is the object, and do I need to draw my hand? Let me try to draw my hand as well. Okay, this is me holding the object. Okay, but the important thing is the object has a mass m, and initially its y coordinate is y initial. All right, let's say I'm lowering this and I'm doing it gradually without speeding up, slowly. I bring it down to here. So this dotted line here represents the later position of the same object. Now the y coordinate is y final or yf, and I stop there. Okay, of course when you first start to move and when you stop, there has to be some acceleration. We're ignoring those things. Okay, we're not really interested in the motion right now. We're just interested in the work. Okay, let's start with that. The work done by two forces which are present here, or relevant, let's say. First of all, I'm holding the book. I'm exerting a force on the object, which is the normal force. Let's call it N or Fn. That's present. And the object has a weight. The Earth pulls it downward, right? The weight. I'm not going to use W, so you don't confuse it with work. I'm just going to write mg, but mg means weight, right? So mg is the weight. Okay, so let's start with the work done by gravity. Work done by Earth, or gravitational force, or gravity. W, G, let's say. Now the displacement is downward, and the force mg is also downward, right? So when two vectors are parallel, their dot product is a positive number. So the work done is simply mg times that distance it moves. All right. So it is force times distance. But what are those? Force is mg. And the distance is whatever you have between these two positions. Now we have coordinates, the y coordinates. yi is greater than yf in this picture, right? So if I subtract yf from yi, I get that distance, displacement in a way. Okay, although I should be careful with the word displacement, because displacement is actually negative in this case. I'm only interested in the actual distance traveled, physical distance, which is positive. Okay, once I realize that the force and the displacement vector are in the same direction, they are parallel, I don't need to worry about signs anymore. I take care of that. I can just use the actual distance traveled, the positive number that represents that distance, which is yi minus yf. Okay, so this number is obviously positive, the actual distance here. So mg is positive. The answer will be also positive. So the work done by gravity is positive. What about the work done by me? Let's say work done by the normal force. I'm going to call it Wn. Okay, work done by me, normal force. It's going to be similar, but remember, Fn is upward. Displacement is still downward. So the two vectors are 180 degrees apart. Cosine 180, negative 1. So this work will be negative. Okay, so this is going to be negative Fn times the displacement. Which I call distance again. So I will have here negative Fn times, this negative comes from cosine 180, right? Negative Fn times, again, yi minus yf. All right? And what is Fn? Remember I said in the beginning, this happens gradually. There's no acceleration. So the net force on the object is 0, which means Fn is mg. According to Newton's second law, the net force is equal to 0. Therefore, Fn is mg. So I can write here negative mg times yi minus yf. Again, yi minus yf is positive, but you have a negative mg here. Therefore, this work, Wn, will be negative. I think in the last video I used the words passive and active. They're not very technical, but you get the idea. So I'm lowering the object. Gravity is doing the positive work. The work I do is negative because I'm just letting it move downward. I'm on the passive side, if you will. Okay. Therefore, the work done by me is negative. And the numerical value, if you had the numbers to plug in, would be actually the same as the work done by gravity, only negative, right? Because the variables are the same. So, what to do with this? Now, I assumed that this change in the position of the object happened gradually without acceleration. Was that really necessary? What if I wasn't even holding it, except for the first time, and then I simply drop it and let gravity take care of the rest? What would happen? Okay, I mean, same picture, same initial position and final position as well. This is the object at yi, but then you let it fall, okay, free fall. It's not going to stop at yf, of course. It's going to have a speed here, which you can find, but it's not important right now. Right? But I'm not holding it, therefore it's subject to gravity, and gravity only. And it's accelerating. But what I'm curious is, will the work be the same? Now, since I'm not holding it, there's no normal force. So normal force, we don't consider the work done by normal force because it's not present, but work done by gravity, that's what I'm asking. Work done by gravity. So what changed? Gravity did not go away. Gravity is still there. And its value pretty much remains constant because this is like a small distance. Gravity doesn't change. It's still mg here. Okay, the displacement is yi minus yf. That's it. So the work done is the same. It is equal to mg times yi minus yf. Still the same positive number we found earlier. Okay, work done by gravity doesn't change. So let's take this expression now and rewrite it in this manner. First of all, let's multiply mg by yi and then by yf. We distributed it, okay? Now, two observations. Number one, we have this initial minus final idea there. And in physics, we are used to this, except that we have final minus initial, okay? The Greek delta stands for whatever you put it in front of, it becomes, it means the initial value subtracted from the final value, okay? So this means final minus initial. Okay, here we have the other way around, but we can fix that easily. We can change the order by pulling out a negative sign. So it'll be negative mg y f minus mg y I. Okay. So the second observation is actually we have exactly the same object, m times g times y, in both terms. So if we give it a name, it's going to be simpler. Why don't we call mgy, just give me a letter, u. Okay, u is very common. So let's use the letter u. Sometimes you will see the letter P.E, but U is also common. So this means that what I have here is actually negative UF minus UI, because U represents M times G times Y. Okay, so we call this the potential energy. We also define it as gravitational potential energy. Gravitational potential energy. Well, it has to have a dimension of energy because it's equal to work, right? So it has to be some form of energy. And now we can write it as delta U, negative delta U. All right, so let's take this. I'm going to rewrite it here. W G is equal to negative delta U. Now this expression will be very common if the forces present are a specific type of force. Okay, what I mean is whenever you see work done is equal to the negative of the change in the potential energy. All right, that applies to a special class of forces. Otherwise, we would not be able to call it the potential energy to begin with. All right, so those are called conservative forces, which means there are also non-conservative forces. But what does conservative mean? Okay, so in physics we have conserved quantities, such as mass, right? It doesn't change, basically. So this will be a similar idea here, okay? We're not we're going to have a quantity that doesn't change, therefore conservative. So let's define what that is. Let me clean canvas here. Conservative and non-conservative forces. And once we understand what these are, we will see what is actually being conserved. Okay, but let me just give you a definition of what such a force means. Actually, there are two ways of defining this. Okay, so the definition, number one, you have a force that you want to find out if it is conservative or not, which can be represented by an arrow, right? Because force is a vector. Okay, this is your force vector. Is this conservative or not? That's the question. So what you do is you apply this force, let's say to an object, and you move the object. Okay, so here's the object. Now it moves along a path. This path could be anything. It could be just a line or a curve, anything. So I'm just going to draw some arbitrary path. Okay, basically you move the object from point A to point B. That's what you're doing. Okay, so just try to think in generic terms. Okay, don't think about gravity or what happened to gravity, friction. Leave it aside. There's only one force, F, and we want to find out if it is conservative or not. And we look at what this force does as the object moves from A to B. That's the idea here. Okay, so we have displacement, we have force. There's not much to think, right? I mean, we can calculate the work done by this. So find the work done by this force F along the path A to B. All right, so let's call it work done by F A to B. Okay, if this notation makes any sense, that's what it means. Well, this will be a number, and it looks like it's going to be a positive number because it's moving in that direction in general, and then there's some angle involved, but still you will end up with a positive work, right? You can all see that, I guess. Now, someone else comes and says, okay, wait a minute. The point is, the goal is to go from A to B. Why do we pick that specific red line as our path? Why don't we pick a different path? I want to take this path and still end up at B. Why not? Okay. Remember when you were loading your truck, you could use a maybe 2 meter long wooden inclined plane or 3 meter, you would end up with the same work. That was that specific problem. But the force would be less if you use a longer plank. Same question here. What if I pick a different path? What will happen to the work? So using the same notation, only change the path number. So this is path number 1. And this is path number 2. Okay, so I'm going to add a letter here. 1. What about work done by F when you go from A to B? Actually, if I put arrows on top of A, they look like vectors. We don't have to worry about that, so let's just get them out. Okay, so A to B, but using the path number 2. Are these equal to each other? Okay. Now that's the definition. If they are equal, then this force F is a conservative force. If equal, then conservative. If they are not equal, it is not conservative. Now, if the task is to carry an object from point A to B, and gravity is involved, as in the case when you're loading your truck, we saw that the work done would not change. So gravity is a conservative force, because you're doing work against gravity, right? And gravity is doing negative work when you're lifting the object, but it's independent of the path. So gravity is a conservative force. Okay, an example of a non-conservative force. In that problem, we ignored friction at that time. Let's not ignore it now. Let's think about friction. Okay, and let's pick a tabletop, and we have an object. Okay, a coffee mug, let's say. We're going to move it around. Okay, we have to push it so that it goes from point A to point B, right? And let's take two paths, one straight and the other one not so straight, maybe like this and then like that. Okay, I didn't want to do it. All right, this is our second path and the red is the first path. Okay, so do I do more work if I take the second path? That's the question. But I said friction, so we're actually trying to find the work done by friction, but I'm pushing it, so I'm doing work against friction. So they're kind of identical problems. Let's mark friction here. Let's use green. Okay, so if I'm taking the first path, right here, if I'm moving in that direction towards B, the friction will be opposing that. So the friction force, the kinetic friction force, would be in this direction, Fk. If I take the other path, when the mug is here, and then when the mug is over there, I have to consider them separately. And then this way. Okay, so the direction of the friction is different, obviously. Fk, Fk. All right, so let's make it simple. Let's mark these. Let's say this is 3 meters, or 3 feet, 4 feet, and 5 feet. Okay, units don't matter right now. But since Fk is the same in magnitude, but only different in direction in these three locations, but the magnitude of the force is the same, I can simply multiply F by that 5 or 3 or 4 and put a negative sign, because it's the opposite direction of the motion. I get the work done. All right. So the work done by friction, let's put a little F here, work done by friction when I take path 1, which is this, will be 5 times that friction force. I'm going to write negative 5 Fk, whatever Fk is. Okay, we don't have to worry about the number value, but it's going to be a negative number, but it's negative 5 Fk. Okay, what if I take the second path? Then the work done by friction, in other words, the energy dissipated by friction, right? If I take the second path, now I have to add these two parts of that trip. It's 90 degrees here. Okay, so the first part will give me negative 3 Fk, and the second part will give me negative 4 Fk. So I'm going to have what? 7, right? Negative 7 Fk. They're not the same, obviously. So it is a non-conservative force. N dot C means non-conservative force. Friction is non-conservative. Okay, so you have the idea, right? I mean, in this course, pretty much every time I say non-conservative force, it will be friction, all right? but the idea is general, based on this. If the work done on an object by a force does not change depending on the path chosen, it is a conservative force. If it depends on the path, then it is non-conservative. And what about the conservative forces? Gravity is one of them. And the force in a spring, which I kind of mentioned briefly last time, is also a conservative force if it's an ideal spring. I think I showed this before, but let me repeat. Let's say we're doing work against gravity by picking a path like this from A to B. And then we pick another path that goes like this. Okay, so along these paths, gravity does the same amount of work, no matter how long the path could be. Okay, I mean, you could pick really something weird like this, but doesn't matter. Gravity will end up doing the same amount of work, and you can always use little increments of only vertical and horizontal when you're doing it. And if you're taking really small increments, the approximation will be good. Like you could go up and right, up, right, up, right, up, right. Okay, you can keep going on like this. As soon as you move too much away from the actual path, go back by turning right or up. Okay, I mean, you can maybe draw it better than me, but you end up with something like this. And you can repeat for this funky graph as well. But the point is, every time you move horizontally, since gravity is always downward, gravity is not doing any work. Okay, so those horizontal movements do not contribute, but the vertical movements contribute. So you add them up. What happens is this net distance, vertical distance between A and B, that's what matters, h. Okay, so if the object you're moving has a mass m, the weight will be mg, and mgh will be the work you do against gravity, and negative mgh will be the work done by gravity. And that will not depend on the path, because you can always pick those little increments and try to approximate the path to that and get the same answer, because always vertical displacements count, horizontal displacements do not count. Okay, and if, of course, if you pick a funky graph like this, sometimes you go up, sometimes you go down. Whenever you go down, the work done by gravity is positive mg, that little increment, right? So mg times delta y, whatever that delta, little delta y here will be, that'll be positive if you're moving down. But if you're moving up, it'll be negative. So those negatives and positives will cancel out. In the end, you will end up with, you can factor out mg, but those delta y's will add up to give only this value h here, in a way. Okay, so that's why gravity is conserved. Now this is, I think, clear. That's the definition of a conservative force. There's an alternative definition as well, so let's call it number 2. The second way of defining it. It also uses the work done by force, but you pick a special path, meaning you don't have points A and B, you just have a loop. So imagine you start here, you complete a loop, okay, no matter how complicated it is, you go back to the same point. Okay, so there's no special point along this path, it's completed loop. If the work done by a force, let's say gravity, or any other conservative force, as you move along this path, if this is closed, so I'm going to call it loop, if this work adds up to what? Can you guess? What does it have to be equal to if the force is to be conservative? Okay, can you guess it? 0. Okay, if the work done by this force is 0. So all those increments, everything, if they add up to give you 0, remember, sometimes positive, sometimes negative, for gravity, for instance, that would be a conservative force. Obviously, for the previous example here of the coffee mug moved on the surface, if you bring it back to A, the friction force will not do 0 work, because friction force always opposes the direction of motion. You will end up with some negative work done by friction, or energy dissipated by friction. It's never 0. So friction is a non-conservative force. So that's an alternative definition. Okay? All right, so let's go back to the potential energy then. Remember, we ended up with, almost half an hour ago, with this equation here. The work done by gravity when the object falls down was equal to the change in the value of U, where U was defined as mgy, the gravitational potential energy. Okay, that's what it is. Now, gravity is the conserved force. So what is the, or conservative force, let's say. The conserved quantity here will be energy. This chapter is called Conservation of Energy, right? So what we do is this. We apply the work energy theorem now. Work energy theorem, which was the total work done by an object. Means find the work done by every force on the object and add those work. You will get total force, total work. That is equal to the what? Change in the kinetic energy. So kinetic energy is 1/2 mv squared. So 1/2 mv final squared minus 1/2 mv initial squared. So take this work energy theorem and use it in this general form we found from the simple example of a free fall. Okay? Now, a free fall, by definition, means the only force on the object is gravity. So for free fall, work done by gravity is the total work. Okay? So that's equal to the change in the kinetic energy. So I'm rewriting this equation, but I'm replacing Wg by W total, which is delta K. So delta K is equal to delta U. Okay, a very important relationship. The change in the kinetic energy is equal to the negative of the change in the potential energy. An equation expressed in terms of changes into energies. Kinetic energy and potential, or gravitational potential energy. Okay, what about the negative sign? Now, wouldn't it be nice if I take delta U and bring it to the left-hand side? Becomes positive, equals 0. Okay, the change in the kinetic energy plus the change in the potential energy is equal to 0. So why don't I write it like this then? The change in the sum of the kinetic and potential energies is equal to 0. Right? Mathematically, I mean, because delta means final minus initial. So the final value of K plus U, whatever that is, let's give it a name. Both are energies. One is kinetic, one is potential. Why don't we call the sum also an energy, letter E maybe, and this stands for mechanical energy. Mechanical energy. But what we have here is delta E is equal to 0. In other words, E final minus E initial equal to 0. In other words, E initial is equal to E final. An object is falling down, its speed changes, its position changes, but what does not change? Its mechanical energy does not change. If it's not changed, we call it conserved. Okay? The conservation of energy, the conservation of mechanical energy when there are only conservative forces. Okay? It's free fall. What if you had an object sliding down an inclined plane and there was friction? Okay? Then this would no longer be true. This is only true when there are no non-conservative forces. Okay, so let's say in general there may be conservative forces and non-conservative forces present. Okay, real life examples. An object sliding down and there's friction here. Okay, so there is Fk, right? What is Fk? Fk is mu k times normal force. Here's the normal force. Normal force doesn't do any work, but gravity is doing work, which is downward. And there's an angle here. You know, classic example. If the object is sliding down, or actually you can give it a push and it may slide uphill, doesn't matter, it may slow down, but still, same idea. In that case, delta E is not equal to 0, okay? Because there are forces which are conservative, like gravity, but there are also forces which are non-conservative, such as friction. So what do? We need to replace this equation by another equation which is more general. That's what we have to do, right? And to do that, we can go back to the work energy theorem again. Remember, so the total work was equal to the change in the kinetic energy, work energy theorem. But this total work is the sum of individual terms, and some of them are due to conservative forces and some of them are due to non-conservative forces. So why don't I express this thing on the left hand side as the sum of two terms, work done by conservative forces plus work done by non-conservative forces. This could be gravity or spring, and non-conservative is pretty much friction. Okay, but that is still equal to delta K. All right, so having separated work like this, now we know that this first term is only about conservative forces, and we have an equation for that, the one that I just wrote here, right? Like I wrote gravity here, but that applies to any conservative force. The work done by conservative force is equal to negative delta U, if U is defined properly. So I'm going to replace this WC with negative delta U, where U represents a potential energy. It could be gravitational, which we know, mgy, or it could be some other potential force that corresponds to a conservative force. It could be the elastic potential energy, which I will define in a little bit, okay? But in general, that's negative delta U. So negative delta U plus work done by the non-conservative forces, such as friction, is equal to delta K. And I do the same trick. I move delta U to the right-hand side, and I end up with delta K plus delta U equal to W non-conservative. Or, using the same notation E here, mechanical energy, the change in the mechanical energy is equal to the work done by the non-conservative forces. okay, or the energy dissipation by friction, okay. Depending on the book you're reading, you may find it defined like that. So, summary. If there are no non-conservative forces present, if there's no friction in the problem, energy initial, mechanical energy initial is equal to the mechanical energy final, or delta E 0, which means E is kinetic plus potential. So initial kinetic energy plus initial potential energy, gravitational potential or other kind of potential energies, is equal to Kf plus Uf. Okay, that's how you can express it. If it is gravity, then it is mgy. So 1/2 mvi squared plus mgyi equals 1/2 mvf squared plus mgyf. That's one way of writing the same equation. Okay, it all comes down to delta E equals 0. Okay, in some problems it may be more practical to write it as EF minus EI. This is what it means. Okay, when we do examples, we'll see what they are. So, this means that I can take this equation here, EF minus EI, and equate it to W and C if there is friction present. If there is friction in the problem, then my equation is not this, but the one on the right hand side. So delta E means E final minus EF. So going back to this problem, for instance, of an object sliding down, or many problems like that, same idea, you can write it like this. 1/2 mv final squared, that's final Kf, plus mgy final. Okay, this is nothing but final mechanical energy minus, now you can write the initial mechanical energy, plus mgy initial. Okay, that would be EI. Okay, if you write it like this, make sure you put the parentheses, or if you're not going to put the parentheses, this plus will be minus, right? So make sure you get that right. But this will be equal to the work done by the non-conservative force. If it is friction, we're talking about negative Fk, the kinetic friction force, times some distance d. That depends on the problem, of course. You determine the distance traveled, okay? So this is what this equation becomes. All right? So that's the idea. What if there are two objects? Now, in the previous chapters, we saw the application of Newton's second law to systems where, let's say, two masses are connected with a rope and the rope goes over a pulley, right? Like the Atwood machine. I think that's the simplest case. So something like this. But there are two masses now. And gravity acts on both, obviously. So we now have to solve this kind of problem. Solving it means finding the acceleration and the tension in the rope, right? This can be solved using energy methods. And if you ignore friction, you just have to use this simpler form, EI equal to EF. But what you have to do is to remember that this E here is not the mechanical energy of one object, but the sum of the two. Okay? So you will have contributions from both the masses. So this will be the total mechanical energy. Okay, so for instance, if you're going to write K in that equation, Ki, we're talking about total initial. So we have 1/2 mvi 1 squared plus 1/2 m1. I'm sorry, this is m2. 1/2 m2 v2i, or vi2, doesn't matter. Okay, so each term in this equation up here is actually the sum of two terms in that aspect. Okay, so keep that in mind when you solve problems with systems of multiple masses. We're talking about the total mechanical energy. You never apply that equation to one mass only. That would be wrong. Okay, so we solved the gravitational potential energy, mgy. What about springs and the elastic potential energy? Now let's remember Hooke's law again. The simplest example you can think of is just a spring attached to a wall, and this side is attached to a mass. And then this may be resting on a frictionless surface for simplicity. Okay, frictionless, no friction. And if there are no other forces present, it's just gravity keeping it there. But I'm not going to write the gravity and normal force. We're not interested in what's happening in the vertical direction, but what's happening in the horizontal direction is what we're trying to see. This position here is the equilibrium. I can always take it to be my origin. I can either push it with an external force or pull it to the right. Push it to the left or right. Then the spring will react, will exert a restoring force. And that force is given by Fs negative Kx. Okay, this is Hooke's law. And I explained this maybe in more detail in the previous video in part 1. Now I say this is a conservative force. Okay, this is a conservative force. Restoring force is a conservative . It kind of acts like gravity in the sense that the work done by the force will be independent of the path. But there's a difference, obviously. This force depends on distance from the equilibrium point, right? Whether right or left. Gravity was not like that, at least in the examples we thought of, like lowering an object, you know. Of course, if you think about an asteroid approaching Earth, that approximation is not valid because the force between Earth and the asteroid is given by an inverse square formula. So that force also depends on distance. But in the lab frame, okay, so it's a constant, mg. Therefore, the potential energy that we obtained from the conserved force gravity was mgy. Okay, a constant force gave us a potential energy in the first order of the coordinate. But in this case, we have a force which is already a function of distance. So what do you expect the potential to be? Okay, so the potential will depend on x, obviously, but it will not be x anymore. It'll be x squared. Okay, so from a force which was constant, mg, we obtained mgy. So we multiplied by a y. Okay, in the case of the Hooke's law, the friction force, we have a constant times x. If you multiply it by another x, using the same analogy, you have x squared. Okay, so the potential energy in the case of the spring will be proportional to the square of the displacement. Okay, so without proving, this is not a calculus-based course. I'm not going to go into too much detail. I can't remember what the book that did there, but let me just give you the definition. The potential energy for a spring, which is called the elastic potential energy, is given by 1/2 kx squared. That k is still present there. X became x squared, but there's also this 1/2 there, okay? So that has to do with calculus. So I believe the book also just tells you what the answer is without deriving. Yeah, they use that triangle in the. Remember in the last video I showed you this force here, how it changes with x. This is F, this is x, and I told you how to find the work done by considering the areas under the curve. So what is the area formula? 1/2 base times height, right? So that 1/2 is also can also be seen from that fact, the area under the curve. Or if you know calculus, that is actually integral, but never mind that, okay? Just take it as a definition, 1/2 kx squared. But pay attention to that form, 1/2 k x squared, okay? So whether you're right or left, meaning to the right here, or to the left of that equilibrium point, means whether x is positive or negative, you're squaring it. So the potential energy is, the elastic potential energy of a spring is always positive. Whereas the gravitational potential energy, which was given as, I'm going to call it UG from now on, mgy. Now this y is your y coordinate. Well, if you're above the origin that you picked, your y's are positive, but what if you're below that point, then your y's will be negative. So the gravitational potential energy can be negative. Okay? It's arbitrary. It just depends on you, where you pick your origin. Okay? So this means also that the problems you solve using the energy method, meaning those equations that I was showing you earlier, if they have a y in the equation, this means you have a reference point. But the solution of the problem, or your final result, should not depend on your origin. Okay? And it is the case. You can try it. You can look at the very simple problem of free fall again. You can measure the distance from the floor, which is your origin, or from the ceiling. Or your initial height, initial position would be your origin, or your final, or any other you can think of. And write down the change in the gravitational potential energy. That will always be the same. So this here, mg y final minus mg y initial. That's delta ug will always be the same whether you pick your origin, the floor, or the ceiling, or any other point. Okay? It doesn't matter. The difference is always the same. Okay, so ug can be negative, but elastic, let's call it us, the elastic potential energy is always positive. So if you plot this, u or us as a function of x, okay, if you remember from analytical geometry, it's something like this, right? Like a ball. If you think in 3 dimensions, that would be a ball, right? But the gravitational potential energy, okay, if you plot it as a function of y, ug, it's something like this. Right? The slope is mg, of course. So it could be negative, obviously. Now, why did I draw these pictures? Visually, actually, it'll tell you something. If you put a marble here, or a ball, what will happen? It's going to slide down. until it hits something here, right? That's what happens when an object falls in gravity. It keeps falling and keeps accelerating until it hits the floor or something, or whatever it's on its path. Okay, it will not go forever, or it will not come to an equilibrium like this one here. In the spring, we had an equilibrium point there. Okay, so this actually mathematical picture gives you a physical picture, if you like to think that way. Because if you look at US, elastic potential energy, it looks like a ball. And if you place your marble here, what's going to happen? It's going to accelerate. It's going to come here. It's going to keep going. It's going to go up, but then fall down again. Okay? Now, if there's friction, of course, it's going to end up in the bottom in the end. That's the final position of the object, right? But the point is, there's the equilibrium here. Okay? Equilibrium point. So that's a very good picture. In general, now I'm not talking about springs or gravity, but a hypothetical case where someone came, in which someone said, okay, hey, I have a potential energy that looks like this. Okay, think of it in 3D maybe. It's like there are two wells and a peak here. So your little toy here, maybe here, over there. And actually, if you are carefully, if you balance it, you may even have it stable over there. But what happens is, if you perturb it a little bit at the top, it's going to start rolling down and it's going to end up either here or there. But for these two balls, no matter how much you shake them or move them around, they always come back to that, okay? So we call these two are stable. We call these two to be stable equilibrium points. And the one in the middle is an equilibrium point, but unstable, okay? You blow on it and then it starts moving. Something to visually identify this. I don't think this picture is in the book, but it's good to know, right? Okay, so that's the potential energy, the second potential energy, 1/2 k x squared. Now, what if the problem involves both gravity and the spring? Then the mechanical energy is kinetic plus potential, but the potential has two contributions, U gravity plus U spring. Okay, so example, a trampoline basically could be symbolically can be thought of a platform sitting on some springs, a couple or just one spring. For simplicity, we can use just one spring, but in reality, you may use more than one for stability, I guess. And you jump on it, okay? So here's you. You jump from some height, and then you end up here, okay? So let's say this is the ground level. Ground is your reference, and your h above your reference, and the platform here is little h. That's the height. And you can ignore the mass here or not, which complicates things, but for now let's ignore it. But you have a mass, m, and you simply drop yourself, okay? So your initial velocity is, let's say, 0. What will happen? You will accelerate and hit this trampoline or platform with some velocity. Call it V1. And you will squeeze the spring. So now the spring will be squeezed and this platform is lower in position and you're still on top of it. But you're here now. Call it H prime. Okay, my distances are measured from the ground level, which is my reference. In other words, that's my y equals 0 point. If you think of the y coordinates like that, that's y equals 0. And I squeeze it. As I squeeze a spring, as I compress a spring, I start slowing down, right? And at the maximum compression, the speed, my speed, is 0. So V final is 0 at that point, but now I'm below that dotted line. Okay? So ignoring air resistance or any other non-conservative forces you can think of, how do we write the equations for this problem? Okay? Equation means delta E is equal to 0. Mechanical energy is conserved. All right? Now, you can either write it as delta K plus delta U, and delta U has the elastic term and the gravitational term is 0. I'm going to write it like that. Or you can write it as E initial is equal to E final, and this means K initial plus US initial plus UG initial. G and S stand for gravity and elastic is equal to kinetic energy final plus elastic potential energy final plus gravitational potential energy final. These two equations are identical, but just a different way of writing. The change in the kinetic energy. Okay. Now, which points am I comparing? So I and F are which points? Because I have 3 points here, right? If this is the initial and this is the final, I can ignore this middle position. Why not? Okay. I can write the equation for that point as well. It's okay. But since I already called this F, let me just take these 2 points then. Okay, so this one, delta K. Now, final kinetic energy is 0. Initial kinetic energy was 0. So the change is 0. Okay, this is nothing but 0. Nothing comes from it. That term is 0. Okay. Now, the change in the elastic potential energy. In the beginning, when you were here, the spring was not compressed. So USI is 0, right? But here, it has been compressed. So there is some positive, it's always positive, elastic potential energy given as 1/2 K. K is a spring constant here. Now I need the square of the distance from the equilibrium point, which is this dotted line here. Okay, so it's not going to be H, it's not going to be H prime, it will be the difference. So I need to write here H minus H prime squared. Okay, that is the elastic potential energy at this position. Delta means you gotta subtract the initial, but initially it's 0. So it is 1/2 K H minus H prime squared. Good. What about the gravitational? What about the change in the gravitational potential energy? Final minus initial. Final position is right there. And my reference is this red line here. I'm H prime above that. So my final gravitational potential energy is mg H prime. mg H prime. I need to subtract the initial gravitational potential energy from that. Subtract the initial, which was mg big H. and these two terms are added. They add up to give you 0. Okay, so this equation here is the equation you will solve. Well, solving means finding one of these unknowns in terms of the other ones. Okay, you can come up with 4 different problems from one equation. This is identical here. Now I said Ki and Kf are the same, so you can get rid of them. They are individually 0. USI is also 0. We only have UGI, which was mg capital H, is equal to final elastic potential energy. That is 1/2 K H minus H prime squared. Okay, it's always positive. Plus mg H prime. Now this equation and this one are the same, just written differently. Okay, these two are the same. So you can think of many other examples where there are both conservative and non-conservative forces present, and also the conservative forces could be gravity and elastic or springs. So you put everything together, okay? And you may have multiple masses. You can also put those together, okay? If there are multiple masses, you add both kinetic energies at a given instant, and that's the total kinetic energy, okay? And if the potential energy requires you to add both gravitational and elastic potential energies, you do so. If there's friction, that goes into the equation that we have over here, right there, okay? So this is the energy method, and pretty much you can solve any problem that you solved using Newton's laws. Now you can solve it using the energy method. It's about solving those energy conservation equations. Now the last thing I want to talk about is power. That has to do with time, okay? Okay, you're doing work, but how much time do you spend doing that work? That is power, P. Okay, so you take that work you do and you divide it by the time you spend doing that work. That is power. In the book it says the average rate of energy conversion or transfer. Okay, so you can also write it as delta E over delta T. It's always some energy over time. So this is measured in joules, this is measured in seconds. So you can say joules per seconds or watts, named after the famous engineer and scientist James Watt. And now there's an alternative form or equivalent form. Now since work is force times distance, if you plug F times D here, you will have D over distance over time, which is velocity, right? So you can take the average force, multiply it by the velocity. That gives you the average power also. That's another form you could use. Remember the dot product? Well, this applies here as well. So if force and V points in different directions, you can use the cosine of that angle. So this is where I'm going to stop, and the next videos will be about momentum and collisions, and so much for work and energy. Okay, so till next time, goodbye.